The next topic is section 4, Rules of Probability 2. This time we are going to study the multiplication rule. Here's a reminder. Previously we studied the conditional probability. From here, the denominator, that's the probability of the condition. Now, if I flip this to the other side, and we get a multiplication like this. This one. Here, flip this to the other side, like this, and that's what we have. From here to there. And this is what we call the multiplication rule. This is the general case. And of course, if I switch those characters, we're going to get this expression. That's theoretically the same. Now, in a special case, if this conditional probability A given B, which I just highlighted in blue, happens to be the same as the probability of A itself, the original probability, then this is the same as this. And if that happens, we say the events A and B are independent. And of course, if this happens, then this probability, which I just highlighted in red, must be the same as this conditional probability too. Compare, because left-hand side is the same. In any case, in this case, we say A and B are independent. And that's a special case that we're going to study closely in the next lesson, in lesson 3. For now, let's stick to the general case. So let's not worry about this anymore. And we're going to study these. And we don't need color coding anymore. So let's go back to the original. Okay. Alright, we'll study the applications of these so that we can get a little bit more solid understanding about the multiplication rule. And also, we're going to study the graphical expression of this multiplication rule, which is going to turn out to be the tree diagram. So the Venn diagram works for addition rule. Likewise, a tree diagram will work for multiplication rule. Here's an example. 3 balls will be selected without replacement from an urn that contains 5 red balls, 3 green balls, and 2 blue balls. So, if I select one ball at random, what is the probability the selected ball is red? Oh, that's easy. That's 5/10 because there are 5 red balls out of total 10. Is that clear to everybody? Alright, now this time we are selecting 3 balls. 1, 2, 3, like that, in that order. So let's change it into selecting the first ball. So R1. Now, am I going to get 5/10? Certainly. I'm selecting my first ball here, and before selecting anything, there are 10 balls there, and 5 of them are red. So 5/10, that's correct. Now, here's my next question. What is the probability that the second row is red, given that the first row was red? You see, red ball was selected already in my first row. And what is the probability now the second ball is red? Now, red ball is out, so I only have 4 red balls now. Previously 5, but 1 is out. So in my second row, there are only 4 red balls. And then there are only 9 balls total. So this probability is 4/9, not 5/10 anymore. Make sense? Now, let us apply this multiplication rule. What is the probability that first row is red and second row is red? Well, I could have used intersection here, but by now everybody knows that means logically the same as and. Now, according to this multiplication rule, you have to multiply these two probabilities, probability and the conditional probability. So this is going to be 5/10 times 4/9. And I'm not going to bother with simplification. Also, let's make one more abbreviation. You have multiplication rule, right? That's associated to and. And that's why many a times statisticians do not bother with AND or intersection and simply use R1, R2 like this. So when you have two sets come like this, kind of like multiplication, that actually means the intersection in statistics. Now, I don't do this in math classes, but this is statistics class, so I'll follow the conventions of statisticians rather than mathematicians. And this is kind of customary, and it's quite useful. As you've seen before, this is for 3 balls, so I don't want to have all those and going further and further and further. Now, if you go to lesson 3, you're going to go to some example like 7 balls are selected, or 14 balls are selected. In that case, you don't have all those and coming. So, all right, 2 balls, all right, we're done. Let's keep using the multiplication rule. Now, how about third row is blue when we know that first and second row were red? What's this? So third row is blue. How many blue balls are there to choose from? No blue ball is out, so 2. Now out of total, what's the total? This is third row, not first, not second. Third row, so 2 balls are selected out. They are red, red. No blue is out, so this is 2/8. So if I put everything together, now use this multiplication rule again, multiply the probability of condition times conditional probability, you're going to get the probability of the intersection. R1, R2, and then B3. So in my first row, red, second row, red, and then third row, blue, what do we get? We get the multiplication. 5/10 times 4/9 times 2/8. And then red, red, blue. Let me expand the font. Maybe I should have done it earlier. I have so many fractions here. It would have been easier this way to read. So what did we just do? We used this multiplication rule multiple times. First row, and then through this conditional probability, we got the second row by multiplication rule. Now this conditional probability, and then we get the third row. Now what if my fourth row is another red? The probability of this and one more. Use the same idea. All these, and then I have to multiply the conditional probability that my fourth row is red. What is it? How many red balls are there now? 2 red balls are out. The third row is blue, so no more reduction. So I have 3 red balls to choose from. Out of total, how many? 7, of course. Make sense? Now what if my fifth row is green? Oops. So one more multiplication of the conditional probability. So how many green balls are there? 3 green balls. And then how many total are there? Does it make sense? And then my 6th ball is red. In that case, what? What do I multiply? Another conditional probability. 3 red balls are out, so I only have 2 red balls to choose from. And out of total, how many to choose? Now I'm down to total 5 balls. you can use this repeatedly like this, and that's a multiplication rule. Now, one way to visualize all this is a tree diagram. No, that's to be too complicated. A tree diagram which looks like this. From the first, I follow a path, and that path is actually the conditional probability, but very first one is the original probability, no difference there. And from here is conditional probability. So one red ball is out. So I have conditional probability for 9th. Situation is now different. Sample size is now different. Now, third row is 2, 8, as we saw before. So, you see, this is conditional probability. Not the same as the original probability. 2 balls are out. Both are red. So I have 8 balls to choose from. And out of those, 2 balls are blue. So there you go. And then if you want to go further, let me extend this. Let's see. Okay, from here, I'll have this. Kind of like this. And then what is this probability here? Out of 5, and then one selected 4, and then no red ball is out, so I still have 3 red balls to choose from. Out of total, now 10, 9, 8, 7 balls. Oh, this is terrible writing. Well, let's erase everything. I mean, this kind of thing can continue, branch out like this. For this reason, people call it a tree diagram. So let's erase all that. So you can do a tree diagram to visualize the multiplication rule, as you saw before, but if you get used to it, you'll be able to use just multiplication, 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 like I just did before. Okay, what are the other problems here? Find the probability to get 2 red balls and 2 blue balls. No, excuse me, 2 red balls and 1 blue ball in any order. So previously, red, red, and blue. So we had to use the multiplication rule. But this time it's a little bit different. 2 red and 1 blue, so it could be red, red, blue, or red, blue, red, or blue, red, red. But each time it's a multiplication rule. You see, this is something we just did. Conditional probability, we just multiply. This one is a little bit different. Second row is now blue, so 2 9th. 2 blue balls to choose from out of total 9. And then red again, so 4 8. And then this is blue, red, red. Now please note that the result is all the same because multiplication is commutative. The denominator, 10 9 8, same. And the numerator, we have some change of order, but 2 red balls, so 5 times 4, 1 blue ball, 2, that doesn't change. So we have all the same thing here, 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 and then if you add them all up, or equivalently multiply by 3, then you get what you want. Talking about multiplying by 3, which is equivalent to how to arrange all these, that's going to be one of more important topics in lesson 3, so please do not forget about those. One more problem here. Find the probability to get at least 1 red ball. I don't need this large fonts now. At least 1 red ball. So let's see. 1 red ball or 2 red balls or all 3 red balls. And that's going to be equivalent of 1 minus the complement probability. And that's going to be 1 minus probability of non-red, non-red, non-red. And then, well, non-red, so anything other than red, so there are 5 non-red, green or blue. And then another non-red. it's going to be easier to calculate like this rather than calculate the probabilities for run red. So red, green, green, red, green, blue, red, blue, blue, all those. And then all the other orders. And then do the same thing for 2 red and then 3 red. It's way too complicated. It's going to be a lot easier if you use complement probability. Okay, we just went through 3 diagrams and then multiplication rules for the conditional probability. As a matter of fact, there's one more picture that I forgot to show you. Here are 2 more tree diagrams, and this one is the original tree diagram for RRB. This one is RBR, red, blue, red, following the path, and then blue, red, red, and as you can see, each time I follow the path, we multiply, multiply, multiply. That's the idea behind the multiplication rule, and the visualization of the multiplication rule is a tree diagram. So theoretical background of the multiplication rule is the conditional probability. Flip over the denominator and we have multiplication rule, we saw that before, and the visualization is a tree diagram. Now, one more little comment and then I'm going to move on to the next topic. One little comment is this one. 3 balls will be selected with replacement this time from an urn that contains 5 red balls, 3 green balls, and 2 blue balls. The only difference between the previous example and this next example is without versus with replacement. What happens with replacement? Select a ball and look at the color, record it, put it back in, reshuffle it, and then take it again. So my second row is identical to the first row. There are still 10 balls to choose from, and then color distribution remains the same because the ball was put back in. Previously, first row was red. Then I have now only 4 red balls to choose from in my second row, but not this time. The ball is back in, so I still have 5 red balls there and total 10 balls there. This kind of thing is a typical example of independent draw. So independent event. Second row is independent of first row. It is not affected by first row because no ball is out. Completely identical situation. More precisely speaking, the conditional probability remains the same as the original probability. So the conditional probability in my second row, it assumes first row happened and that was the result. But then again, that result didn't change anything because the ball was put back in. So conditional probability and original probability are the same. And then we have this straight up multiplication rule. In that case, computation, oh, that's not that important. Computation is like this. Now let's compare that. We have conditional probabilities, so things changed, but here, no change. Original red, and original blue, that's it. Here, original red, but this one is conditional. Total number of balls changed. And let me increase the font. They are fractions, so it's easier this way. And then number of red balls to choose from, that changed. But here, no change. So without replacement, they're dependent. With replacement, they're independent. And that's why things are easier. In this case, in independent case, we have, excuse me, I don't know what I did, but momentarily I lost the screen, so I have to reboot. Sorry, we are back. Well, okay, all right. So we are done with these 2 topics. And then we are going to talk about the next example and Bayesian analysis in separate videos.